So everybody knows we can flush a toilet with a big bucket of water, but could we flush a toilet by peeing really hard? Toilets in America flush with around 1.28 to 1.6 gallons of water, or around 4.8 to 6 liters. So we'll assume the upper limit of 6 liters is required to properly flush a toilet. The human bladder can only hold around half a liter of fluid, so that amount by itself is not sufficient to flush a toilet. But assuming you have male genitals, we can bring over 11 other homies to make up the difference. Unfortunately, it's not that simple because peeing takes time. Time that your toilet would use to stabilize the water level and prevent your toilet from actually flushing. You could see this by slowly flushing your toilet, but I wouldn't recommend it because that's a waste of water. So instead, we'll need to model the rate of fluid leaving the toilet and the rate of fluid n number of people can produce. Luckily, a couple hundred years ago, some dude invented a very nice, really simple equation that can accurately model fluid flow. But for the sake of my own sanity, we'll have to use some simplifying modeling assumptions. First, we'll assume the toilet bowl is in the shape of an elliptical cone because I can't be bothered to measure the contours of my toilet. We'll assume any fluid leaving the toilet just magically disappears. We'll assume that the average rate of pee is constant because upon observation, most of the pee you pee out lands in the same area, meaning it has a relatively constant velocity. We'll draw our coordinate axis like this so we can work in one dimension, and of course, there is no stress tensor because peeing is an activity that relieves stress and is stress-free. We know the rate at which the volume of fluid inside the toilet increases is equal to the amount of fluid coming in minus the fluid going out. And we know that the fluid going out is equal to the density of the fluid times the volumetric flow rate, or area times velocity. We also have Euler's equation, and finally we can probably assume that the velocity field is separable because of conservation of mass or something. So the velocity is just the velocity at the end of the pipe scaled by the cross-sectional area. We can plug in this final assumption into Euler's equation to obtain a nice and friendly expression for our velocity. And for the sake of my sanity, we can check that in the limit that h1 gets really big and the acceleration really small, the system becomes a reservoir and velocity approaches the root of 2gh, which everybody that has taken high school physics should be familiar with. And it's at this point that I upset every mathematician because I'm going to have to use a numerical... Boo! Okay, so I wanted to do an analytical solution, but I'm stupid. The problem is the height of fluid in the toilet bowl will probably end up as some exponential of the speed u, so we'd probably end up using a bunch of Taylor approximations and stuff, so might as well cut out the middleman and go straight to computational methods. And so, very boringly, we'd need to bring around 119.5 homies to flush a toilet in around 10 seconds, but you might want to round up to 120 to make sure. I chose 10 seconds because after that point, the rate of pee would probably slow down and be insufficient for flushing. Now this results in 120 times 20 milliliters per second for 10 seconds, or 24 liters, or around 6.34 gallons, which is around quadruple the amount of fluid you'd need to use in a conventional flush. But you weren't going to use that pee for anything anyway, so I guess it technically saves water. Just make sure the guys up top know how to aim.